Hi, my name is Michael Kamp and I'm presenting joint work with Pascal Welke, Florian Seifert and Stefan Wrobel on HOPS, Probabilistic Subtree Mining for Small and Large Graphs. The problem we are tackling is counting patterns in large graphs. That is, we have a pattern graph H and a large graph G, and we want to count how many times we can embed our pattern into the large graph. So why would we want to count patterns? One application is that we want to find substructures that are common or frequent in a larger graph. For example, certain social structures in a social network. Another application is that we have a database of graphs and we want to find subgraphs that are frequent in all the graphs in the database. For example, the graphs in our database could be molecules that represent drugs, and we want to find substructures that are common to all these drugs, which then indicate active components. Formally, we have a labeled large graph G and a labeled pattern graph H, and we want to estimate the number of subgraph isomorphisms from H to G. That is, how many subgraphs of G can we find that are isomorphic to H. We denote the set of embeddings by CH of G, and the number of embeddings is the size of that set. The problem is that exact counting is slow. Indeed, it's Sharp-P complete and only exponential runtime algorithms are known. So we need estimation algorithms. Führer proposed in 2014 to use importance sampling to estimate the pattern count, and they showed how to do that using an ordered bipartite decomposition of the pattern graph, and for this they could prove that you obtain a fully polynomial randomized approximation scheme, or FPRAS, for graphs that are Erdős-Rényi. Then Ravkic et al. Showed in 2018 that this approach also works in practice. Importance sampling is a fairly simple idea where you find a partial embedding of your pattern and estimate the probability pi of having found that certain embedding. Now, if your estimator z is exactly 1 over pi, then the expected value of your estimator is exactly the amount of possible embeddings. Now you can easily iterate this estimator k times and average the estimation to reduce the variance, so the more iterations you make, the more accurate your estimation becomes. To estimate this pi, you can pick one node in your large graph G at random, and then count how many embeddings would be possible from that node on. However, for arbitrary graphs, this is still expensive. In particular, Führer et al. Provided an approach to estimating this probability and thus getting an efficient approximation if your pattern graph can be decomposed into an ordered bipartite decomposition. That is, if you can partition your nodes into blocks V1 to VL, where there is no connection within a block. For each node within a block VI, there's only one connection from this node to any previous block, and all other connections are to subsequent blocks. And of course, computing such an OBD is hard. Moreover, the approach requires sampling a maximum matching uniformly at random, which is expensive. So the overall runtime after k iterations is, of course, depending on k, but also depends factorial on the maximum degree of G. And the maximum degree of G can easily be in the thousands for larger graphs. And also it depends on the size of the OBD of H. Now, if you look closely at the OBD, then you might notice that it looks pretty much like a tree. And this is because trees are natural examples of an OBD, so they are trivially already an OBD. So our approach is to restrict the patterns to trees. In that case, we do not need to compute an OBD since trees are already OBDs. And also we showed that in this case you do not need an explicit matching algorithm because a greedy embedding of a tree is already sufficient. Still, since trees are technically OBDs, all the guarantees from Führer et al. Still apply. So this approach remains an FPRAS for Erdős-Rényi graphs. The runtime now only depends linearly on the degree of G instead of factorial and on the number of vertices in our pattern. Notice that the size of the large graph G does not matter at all. So how does the HOPS embedding algorithm work? First, you select a tree root in your pattern uniformly at random, and then find a node in your large graph with the same label, also uniformly at random, and fix those two. And then you select the child nodes of your root and try to embed them in the neighbors of the selected node in G. And you count how many times this is possible. And as soon as you found an embedding, you can continue this step with all the children of the nodes you've already embedded. So you can see that in a simple example where we already fixed the root, and we then expand our embedding into the neighborhood in G, and in each step we check how many embeddings are possible to get our count, and then take one greedily and embed. And notice that if at some point we cannot embed, then we would count this as an unsuccessful trial and report z equals to 0. This introduces a one-sided error because we can then only overestimate the true number of embeddings. The theory so far suggests that the HOPS algorithm should be fairly fast, but the question is, how accurate is it? To find that out, we have conducted experiments on 4 medium to larger size graphs where we compare the HOPS algorithm to the exact counting algorithm from Ullmann, as well as to the natural baselines, which are the practical applications of the FIRA approach by Rafkic from 2018. We also want to estimate the runtime of our algorithm on very large graphs where the exact algorithm is not applicable anymore, and also where the Rafkic approaches fail. So for that we have picked 3 very large graphs and report runtime results as well. But let's first look at the accuracies. In the experiments you see on the right side, we have plotted the relative error of each baseline with respect to the exact counting over time, since with more iterations the estimate becomes better. Notice that the HOPS algorithm not only has a lower relative error than the baselines in all 4 experiments, but also a lower variance. And it reaches this low error a lot faster than the baseline algorithms. In a second experiment, we want to analyze the runtime of HOPS on very large graphs and its behavior with respect to the pattern size. For that, we report multiple runs of our HOPS embedding algorithm for a certain pattern size on each dataset. And as you can see, the runtime per iteration indeed is linear in the pattern size. However, the slope of this linear relation is different for different datasets. That is natural, since the maximum degree of the graphs in which we try to embed plays a role here. So if we show the runtime per iteration times average degree of G, then we see that the linear relation is actually similar, except for the Amazon dataset. Now, the Amazon dataset has a very, very small average degree, so for many embedding attempts, we will not be able to find an embedding, and the algorithm stops prematurely, reducing the runtime even to something sublinear. Notice that for these graphs, not only is the exact algorithm too slow to produce results in acceptable time, but also the baselines cannot produce any results for patterns larger than 20. So the HOPS embedding algorithm indeed establishes a new state-of-the-art with respect to the pattern size. As mentioned in the introduction, a second application of the HOPS algorithm is frequent subtree mining. Here we are not interested in counting the number of embeddings in a graph, but rather we have a database of many graphs, and we are interested in the frequency of a tree pattern in this database. To apply the HOPS algorithm to this problem, we run it for each graph for a certain number of iterations. If we find an embedding, then we know that there is one, and we can increase the frequency count for that pattern by 1. If we haven't found a single embedding in all the k iterations, then we assume that there is none, although we could be wrong here. This estimation with a one-sided error is known as probabilistic subtree mining. And the current state-of-the-art algorithms are the probabilistic subtree and the boosted probabilistic subtree mining algorithm. Thus, we compare HOPS to these two baselines on a set of 6 standard graph mining datasets. The results show that the HOPS algorithm not only finds substantially more patterns than the state-of-the-art in the same time, but also that on some datasets, it does so faster by orders of magnitude. In conclusion, I hope I could convince you that the HOPS embedding algorithm is fairly easy to implement, very fast, and most importantly, independent of the target graph size. It is accurate and outperforms the state-of-the-art estimation algorithms, and it allows to estimate the number of trees in cases where either the graph or the pattern tree is too large for the state-of-the-art to produce any result within a reasonable amount of time. Moreover, it allows to find frequent subtrees orders of magnitude faster than the state-of-the-art. With this, I thank you for your attention, and I'll be happy to answer your questions in the Q&A session.